Hi everyone, this is Facundo Molina from University of Rio Cuarto in Argentina, and in this talk I'm going to talk about Fuzzing Class Specifications, a work in collaboration with Marcelo Damorim and Nazareno Aguirre. So to start, let me describe a typical automated analysis scenario. Usually when we want to analyze our programs, we use some program analysis tool that provide us with some feedback on the behavior of our programs. When we incorporate a specification of the intended behavior of the software, the analysis performed by these tools can be considerably improved, allowing us to catch more bugs or to have better guarantees on the behavior of the programs. Unfortunately, specifications are seldom available, and moreover, trying to provide them can be a very challenging and time-consuming task. This situation illustrates the relevance of the Oracle problem. That is essentially the challenge of distinguishing between correct and desired software behavior from incorrect and undesired software behavior. There are many approaches that one may take to the Oracle problem. One is to try to manually provide a specification using some formalism and trying to capture the expected behavior of the software. Another is try to use what are called implicit oracles, which essentially has to do with trying to analyze the software in order to reveal general software faults such as buffer overflows or null pointer exceptions. And another approach is to try to derive the oracles from existing software elements such as a previous version of the software. Our work focuses in this last approach to the problem and in a particular type of oracle derivation activity called the specification inference. In a specification inference, we take a program under analysis and some other existing elements accompanying the software, such as executions of the system, comments accompanying the code, or documentation of the software. And then we use a specification inference tool that reports some assertions that are consistent with observations made in the provided elements. In our work, we use executions of the system in order to infer specifications, and our goal is to infer a specification capturing the current program behavior. So we may ask, why is it useful to have a specification capturing the current behavior of the system? Well, inferred specifications can have many applications. For instance, in the context of regression testing, as we know, as time goes on, the programs evolve and one may be interested in checking whether the original behavior of the program is preserved. In the context of differential testing, when we have different implementations of the same functionality, we may be interested in checking whether these implementations respect the same specification. In the context of program comprehension, we may try to infer specification that will allow us to explain what is happening at a particular program point, and so on. In fact, Daikon, a very well-known tool for specification inference that is a very active project with more than 20 years of development, it's being used for many other applications, including program repair, fault localization, and many others. So Daikon infers specifications through a technique called dynamic invariant detection. It takes as input a program under analysis and a test suite exercising these programs, and then from a set of provided candidate assertions, it infers likely invariants that are essentially assertions not falsified by the test suites. This approach has some limitations. On the one hand, it has a limited expressiveness. The properties that are reported as invariants are limited by the set of provided candidate assertions that are typically simple arithmetic and logical expressions. And although these expressions can be manually extended, it is not a straightforward task to do. On the other hand, it also has a weak precision. It typically reports false positives and redundant assertions among the invariants. So in order to overcome these limitations, other recent techniques have been proposed, in particular GAssert and EvoSpecs. These approaches differ from Daikon in several aspects. For instance, regarding the underlying technique, as Daikon uses dynamic analysis, these approaches uses evolutionary computation. GAssert uses a co-evolutionary algorithm, and EvoSpecs uses a single objective evolutionary algorithm. Also, regarding the assertion strengthening approach, DICON uses an ad hoc template-based approach, and essentially it doesn't instantiate some assertions that can be derived from previously discovered assertions. In the case of GAssert, it uses code mutation in order to retain in the evolutionary process those assertions that are able to detect mutants, and in the case of EvoSpecs, it uses state mutation with the same purpose. And finally, these tools differs in the assertion language they use. DICON use simple arithmetic and logical expressions. In the case of GAssert, it extends the language of DICON with further arithmetical and logical expressions, and EvoSpecs focuses on quantification properties and also in properties that can be obtained through object navigation. These techniques have achieved some improvement over dynamic invariant detection. For instance, regarding expressiveness, as DICON uses a provided set of standard assertion templates, the evolutionary approaches are able to explore a larger search space of assertions thanks to the evolutionary processes that they involve. Regarding precision, DICON reports some false positives and some redundant assertions, and the evolutionary approaches are able to report less and stronger assertions thanks to the assertion strengthening approaches they involve. However, these techniques still introduce some limitations. The evolutionary approaches are expensive, and also the assertion languages that they use are difficult to adapt to support further assertions, since the components that are part of these evolutionary processes are specifically designed to deal with the assertion languages they support. So our research arises from whether we can improve DICON to overcome the above limitations without introducing the issues of the evolutionary approaches. In order to improve dynamic invariant detection, we need to focus on two aspects. First, we need to find a more convenient way to extend the set of candidate assertions through some kind of producer, and second, we need to find a mechanism to report the most relevant assertions through some kind of selector. So, in order to improve dynamic invariant detection, we propose SpecFuzzer. The first goal of our technique is to remove the need of manually specifying new assertions. To do so, we define an assertion grammar capturing a specific assertion language, and then we provide this grammar as input to an assertion fuzzer that allow us to produce thousands of candidate assertions. These assertions are then fed to DICON that reports many likely invariants, and our second goal is to report only the assertions that are more relevant. To do so, we implemented a mutation-based assertion selector that allows us to report the most relevant assertions. The first component that we developed, the Assertion Fuzzer, takes as input a base assertion grammar that can be straightforwardly adapted to our need. Then, from the target class, we perform a grammar instantiation step in which the terminal symbols of the base grammar are extended with symbols taken from the target class. And then we use an assertion fuzzer that it is essentially a grammar-based fuzzer that, through explorations of the production rules of the grammar, is able to produce thousands of candidate assertions that are included in the candidate assertions considered by DICON. Then, in the second component that we developed, in order to reduce the reported assertions to the most relevant ones, we first take the target class and use a mutation analysis tool in order to provide mutants from this class that represents artificial bugs. And then we use an assertion selector that works as follows. It takes as input the likely invariants produced by DICON and also the mutants produced by the tool. And then the assertions are grouped according to the mutants they kill, and finally a unique assertion for each partition is reported. The intuition here is that assertions killing the same set of mutants are considered equivalent. For instance, when analyzing a method implementing the minimum operation of two values, these two assertions killed the same set of mutants, and thus only one of them was reported. Another intuition here is that assertions that do not kill any mutant are considered irrelevant. For instance, for the same subject, this assertion that always returned true was unable to kill any mutant, and then for that reason was discarded. So in order to evaluate our approach, we took 43 subjects from the evaluation of the previous works, GAssert and EvoSpecs, and then we produced the ground true assertions for each one of these subjects, obtaining a total of 65 assertions. Then we executed SpecFuzzer for each one of these subjects, and we use as a base grammar a grammar capturing the assertion languages of DICON, GAssert, and EvoSpecs. And then we focused our evaluation in 3 research questions. First, we analyzed how effective was grammar-based fuzzing at generating relevant assertions. We also analyzed the effectiveness of mutation-based selector for removing redundant and irrelevant assertions. And finally, we compared SpecFuzzer with alternative techniques. In order to evaluate the effectiveness of grammar-based fuzzing, we took the 43 subjects considered in our evaluation, and then we execute only the first part of our technique, that is, the Assertion Fuzzer and the dynamic invariant detector DICON. After executing this first part, we obtained more than 20,000 assertions, and we were able to detect 40 assertions of the assertions present in the ground truth. In summary, the Assertion Fuzzer allows us to detect 61% of the ground truth assertions. In order to evaluate the performance of the assertion selector, we took the output of the previous step and then we incorporated the assertion selector in order to reduce the reported assertions to the most relevant ones. After doing this, we were able to considerably reduce the number of reported assertions. We obtained 975 assertions in this second step, while detecting 34 assertions of the ground truth assertions. In summary, the assertion selector reduced the reported assertions by 95%, allowing us to discover 52% of the ground truth assertions. But as we can see here, some of the assertions were missed during the selection process. In particular, we missed 6 assertions. So to better understand why the selector discarded some of these assertions, we analyzed each one of them. And for example, one assertion was related to a pop operation in a stack implementation using array. In this case, this operation always inserted a null value in the position where in the previous top position, and this is an assertion capturing such behavior. Unfortunately, since there was no mutant modifying the null value after the pop array update, our selector discarded this assertion as irrelevant. Similarly, in another case study, we had a routine that always returned 1, -1, or 0, and this was an assertion capturing such a behavior. Again, since there was no mutant making this method return a value other than 1, -1, or 0, our selector discarded this assertion as irrelevant. So the effectiveness of the assertion selector may be improved considering further mutation operators. Finally, we compare SpecFuzzer with the evolutionary approaches. So as we mentioned, SpecFuzzer was able to infer 34 assertions of the ground truth. When we executed GAssert, we were able to obtain 18 assertions of the ones present in the ground truth, and most of them were also inferred by SpecFuzzer. More precisely, SpecFuzzer only missed one assertion produced by GAssert. When we executed EvoSpecs, we obtained 25 assertions of the ground truth, and again, most of them also produced by SpecFuzzer. More precisely, SpecFuzzer missed 8 assertions of the ones produced by EvoSpecs. In summary, SpecFuzzer was able to infer 52% of the assertions in the ground truth, while EvoSpecs and GAssert were able to infer 38% and 27% of the assertions, respectively. So to conclude, I would like to highlight some remarks. First, the Oracle problem is a relevant problem in software engineering that has gained a lot of attention in the last years, and developing new tools and techniques to tackle the Oracle problem can help us to improve many program analysis tasks, including program repair, fault localization, among others. SpecFuzzer uses grammar-based fuzzing and mutation-based selection to effectively improve dynamic invariant detection. Moreover, we use fuzzing as a mechanism to produce and generate candidate assertions, as opposed to its typical usage, inducing failures. And finally, specification inference can still be improved regarding scalability to be able to handle larger programs, regarding expressiveness to be able to detect and infer complex assertions and specifications, and regarding precision to reduce the number of false positives and redundant assertions. So this is how my talk concludes. Thank you very much for listening, and I'll be happy to see you in my live presentation and to answer questions.